All right, well, welcome everyone to the final presentation in Quasi's 2016 Spring Cyberseminar series, the Water Energy Nexus. My name is Emily Clark, and I'm the Communications Manager at Quasi. This series has been hosted by Bridget Scanlon at the University of Texas at Austin. And so before we begin, I just want to thank Bridget again for putting together a great spring series for us. I hope you all have enjoyed it. And just a reminder that all of the talks in this series have been recorded and posted to the Quasi website. So if you missed one and you'd like to go back and watch one, I will put the URL in the chat box where you can find it. So I'm going to turn it over to Bridget to introduce the talk.
Hi, folks. Thanks for logging in, and Vince Tidwell from Sandia National Labs and I will talk today about water energy issues focusing on electricity. And I think, Emily, are you going to switch the, oh yeah, great. So we're focusing on electricity today. Electricity is a secondary form of energy, and in the second slide, then I think they're getting cut off a little bit at the top, Emily. I don't know if you can change the resolution a little bit. Thanks. So here I try to describe the linkages and feedbacks between energy and water. And we use energy to extract, treat, and transport water. And then we use water mostly in thermoelectric cooling plants to create energy, and then most of that water returns to the system. So the withdrawal rates are high, but very little low consumption rates. And then during a drought, energy demand is higher during heat waves and drought periods when water supplies are low, so that can create problems. So during the heat wave in Europe in 2003, this shows a temperature diagram. You can see the extremely high temperatures in France, and the reported deaths were about 70,000, and these were attributed to nuclear power plants shutting down because the temperature of the cooling water exceeded the design limits of the plants, and also discharge temperatures exceeded regulatory limits. So that emphasizes the importance of water and energy during drought periods. So here I show the relationship between water and energy, and the upper half of the diagram focuses on water use for energy, and the lower half on energy for water. So on the upper half, you can see that water is used for fuel extraction. And last week we talked about water use for hydraulic fracturing for oil and gas production from shale gas plays. Then water is also used for refining fuels, and today we're going to focus on water use for electricity generation for cooling in steam and thermoelectric power plants. I'm not going to talk much about energy use for water, but I know Vince Tidwell will talk a little bit about that in the second half of this lecture. So just to put things in context, when we spoke last week about water use for hydraulic fracturing, so water used to produce natural gas using hydraulic fracturing in the Marcellus and Eagle Ford shale plays represents about 6% of water consumption at power plants that use that natural gas to generate electricity. So this just gives you an idea of the relative amounts of water. So I'm going to try to cover these different topics, basic differences between water and electricity systems, what can we learn from energy flow or Sankey diagrams, what are the dominant controls on water withdrawal and water consumption in power generation in the US, and then talk about the water footprint of electricity generation in the US, and lastly, just briefly describe the vulnerability of electricity generation to drought using Texas 2011 drought as a case study. So some fundamental differences between water and electricity systems. We can readily generate electricity, but we can't really generate water. However, we can generate fresh water from saline water using desalination. From a storage perspective then, it's very difficult to store electricity. There's some work being done in battery storage, but it's not really economical at this stage. And there are significant advances in this area, but it's not widely used. Whereas we can store water in reservoirs and aquifers. So because we cannot readily store electricity, then electricity supply needs to meet demand at the minute or second level, and that becomes a critical issue during high peak demand periods, during drought conditions. For example, in Texas, it's early August. We can readily transport electricity through the electric grid, but man-made pipeline systems for transporting water are fairly limited. And we have the natural system for transporting water through rivers and aquifers, but man-made systems are probably most developed in California. So here you can see the U.S. electric grid, and you can see the Western interconnection system and the Eastern interconnection system. So that's valuable. So if you have a shortage in one area, they can get electricity from another area because of the extensive grid system. However, Texas is on its own, and through the ERCOT system, Energy Reliability Council of Texas, and so we have very little interconnection with the national grid systems. So that means that maybe we're more vulnerable during drought periods. So because we cannot readily store electricity, one way to cope with this issue is to have excess capacity. So the reserve margin, this is a map of the reserve margin for different regions of the U.S. Produced by the Energy Information Administration, EIA, for summer 2014. And so the upper number is the estimate of the reserve margin, the lower number is the target. And the reserve margin is defined as unused available capacity of an electric power system at peak load as a percentage of the total capability or capacity. So you can see in most areas the estimate of the reserve margin far exceeds the target, but in Texas they're pretty close. And so we may need to increase our reserve margin to provide additional buffer during drought periods. In 2012, the reserve margin for California and the estimate and the target were very similar in California, but since then they've doubled their estimate and now are twice the target. So the second question I wanted to address was what can we learn from energy flow diagrams? So A.J. Simon and Suzanne Singer and others at Lawrence Livermore National Lab put out flow charts each year showing the production of energy and the distribution through the system. These are also called Sankey diagrams, after an Irish guy in the late 1800s developed these systems to analyze energy flow for steam turbine locomotives. And the width of the lines reflects the quantity of energy moving through the system. So on the left side of the diagram, we have the sources of energy. And here I'm just showing a few sources, the renewable sources. And the units are in quads, quadrillion British thermal units, BTUs. So in 2014, the US produced approximately 98 quads of electricity. And one quad is equal to 10 to the 18 joules. So because it's almost 100 quads, then the distribution of energy sources on the left reflect approximate percentages of energy by different sources. And then the lines then link up, and you can see that in 2014 we had almost 40 quads of electricity generated, and then about 12 quads of usable electricity that went to the various users, the residential, commercial, industrial, and transportation sectors. So in this diagram, then you can see that some of the energy goes through electricity, but then, for example, solar then goes directly, a fraction of it goes directly to residential, and some geothermal goes directly to residential and commercial, and biomass to industrial. So this diagram then adds the fossil fuels and natural gas, coal, and petroleum. And if we just look at natural gas as an example, you can see we had generated 27.5 quads of energy from natural gas, and about a quarter to a third of that went to electricity, and then 5 quads went to residential directly, and 3.6 to commercial, and almost 10 to industrial. So natural gas is very flexible and is used in different sectors. Coal then mostly goes through electricity to different users, and petroleum is mostly to transportation and some to industrial. So then on the right then you can see that we generated about almost 40 quads of usable energy from these different sources for these different sectors. And then the residual then, oh sorry, I won't jump too fast. The residual then, about 60 quads, is rejected energy. So there's a lot of energy that we generate that we can't use. And you can see that about 26 quads of that is from electricity, 21 from transportation, and then you can see smaller amounts from the other end-use sectors. So this gives you an idea of the various energy sources, renewable and non-renewable, and then how much goes through electricity and how much goes directly to various sectors, and how much is rejected energy or waste energy in the system. So DOE has produced an excellent report, the Water Energy Nexus Challenges and Opportunities in 2014, and there they combined the energy Sankey diagram and also developed a water Sankey diagram and showed the linkages between the two. I don't have time to go into the details of this, but I would just like to point out, so the energy is in quads and the water use is in billion gallons per day, and you can see one of the primary areas of connection is electricity generation and thermoelectric cooling, responsible for a lot of the water withdrawal in the system. And then the other major water use is irrigated agriculture. But if the link to this report is shown on the bottom of this diagram if you want to look at more detail. So next I want to talk about the controls on water withdrawal and water consumption to help understand how these things work. So here I'm showing a steam turbine power plant, a schematic for a steam turbine power plant. So thermoelectric plants or steam turbine plants use different fuel sources to heat water, and examples of the fuel sources include coal, nuclear, fission, or natural gas heat sources. So water is heated in this boiler system and creates high pressure steam that then drives a turbine and generates electricity from that. And then this water needs to be cooled on the other side in a condenser in order to be reused. So this water system on the left here is a closed loop system, and water is cooled then by different types of cooling systems. In this diagram, I'm showing a once-through cooling system, which means that we draw water from a river or a large lake, and it moves once through the condenser and then cools the steam, and that the condensed steam then moves back into the boiler and moves through that system. And the heated water then returns to the river or the lake. So the water withdrawal for these once-through systems is pretty high, but most of that water is returned to the system at a slightly elevated temperature. And so these once-through systems are characterized by large water withdrawals and low water consumption. So about 90% of the electricity generated in the US is thermoelectric or steam electric generation, and so requires water or some other form of cooling in the system. So this is one of the cooling systems that's available, and then the other system is a cooling tower, and the water withdrawals for a cooling tower are very low, orders of magnitude less than a once-through system, and the water is recirculated from the cooling tower to the condenser many times, and then some of that water then is eventually discharged after it's been cycled through numerous times. So cooling occurs here by most of the water that's brought into the cooling tower is evaporated, and the cooling is by latent heat of evaporation. So this cooling tower is characterized by low water withdrawals and higher water consumption because more evaporation than a once-through system. So they're the two dominant types of water-cooled systems, and more recently also we have air-cooled plants, and these use air instead of water, but water is more efficient, and because air cooling is less efficient, then there are more emissions associated with air-cooled systems. So Tim Deal and Melissa Harris and others at the USGS have done detailed studies on power generation and water use in the last couple of years, and this is some output from one of Tim's reports. And these are Sankey diagrams for different types of plants. So on the top left is the typical nuclear plant, and you can see the total heat in the system on the left, and then NE is net electricity generation, and that's reported, and then condenser duty is the waste heat that is rejected from the system. So there's no heat loss through a stack in a nuclear plant. Combustion steam plant is shown on the lower left, and these would be coal, nuclear, or natural gas steam plants, and total heat moving into the system, net electricity generation, and then losses through the stack, SL, stack losses, or losses from the equipment to the atmosphere, and then the condenser duty or the waste heat also shown. And then on the right then, Tim shows a combined cycle plant, which is more efficient than a typical traditional steam turbine plant, and these are used with natural gas. So the total heat is coming in on the left, and the CT is the combustion turbine part, and they combine combustion turbines and steam turbines. So many natural gas combined cycle plants have two combustion turbines to one steam turbine. So the waste heat from the combustion turbine then is used to drive the steam turbine part, the CA, and so that means that there's less wasted energy and the efficiency is higher. So you can see that the condenser duty is much smaller than the nuclear or the steam plants. So we rely on operators or utilities to report water withdrawal and consumption to EIA to get an understanding of the water use for power generation. But Tim and others have evaluated these numbers using a heat and water budget, combined heat and water budget equation. I'm not really going to go into the details of this, but would refer you to Tim's work, but just briefly, the condenser duty or the waste heat is equal to the total heat from the fuel source minus the net electricity generation and minus different losses such as steam and losses to the atmosphere, and then XH is the exported heat through a combined heat and power plant. So sometimes they use the waste heat then to run heating or cooling systems. For example, in Austin, the airport has this combined heat and power system. So he evaluates he estimates the water use using this heat budget and then a related water budget equation where he takes the heat of evaporation, condenser duty times the evaporation ratio to estimate how much water would be withdrawn and consumed, and uses these then to evaluate the reported data from EIA, and this is described in his report. So trying to describe the controls on electricity generation. So here I showed the 2014 data from EIA. So we generated 4 terawatts of electricity in 2014, and here you can see the distribution of the different energy sources. Almost 20% was from nuclear, almost 40% from coal, and almost 30% from natural gas. Hydro was 6%, and wind and others were 8%. So then these different fuel sources are related to different generator technologies or prime movers. So coal and nuclear typically use steam turbine power plants, and natural gas can also use steam turbine plants, but natural gas, as we described in the previous diagrams, can also use combined combustion turbine with no water requirements with steam turbines in a combined cycle plant. And so there were 24% of the electricity generation in 2014 was from natural gas combined cycle plants. And then there are also some gas turbine plants, 2% that don't use any water, and then hydro and wind, which don't require any water. And lastly, then, this shows an approximation of the distribution of cooling systems, about 40% once through and 40% recirculating cooling towers. So you recall that once through cooling systems have large water withdrawals and smaller water consumption, whereas towers have much orders of magnitude lower water withdrawals and slightly higher water consumption than once through systems. So this gives you an idea of the electricity generation distribution in 2014. And here we show the evolution of the US power plant fleet by fuel source over time. So you can see from the 50s, coal gradually increased, and in 2014 represented about 30% of electricity generation. Natural gas increased initially and then leveled off from the mid-70s and then increased again around 2000. And petroleum, shown in red, represented 4% in 2014, hydro 9%, wind 6%, and solar almost 1%. So this shows how the power plant fleet has evolved over time by fuel source, and and then this is by generator technology or prime mover. So you can see in the past 50s, 60s, steam turbine plants were the dominant generator technology used, and then more recently, around 2000, then we have an increase in natural gas combined cycle plants, and they now represent 23% of generation in 2014. Gas turbines are also increased around 2000, and they don't have any water requirements. And then the others are renewables. So the water footprint of electricity generation, this is based on USGS data for 2010. And on the left, I'm showing water withdrawal, and on the right is water consumption. And you can see that in 2010, thermoelectric power generation represented about 50% of water withdrawal in the US, about 130 billion gallons per day. And on the right, then, you can see that thermoelectric electricity represented about 4%, almost 3.6% of water consumption. So it represents a large water withdrawal, but most of that water is returned to the system, and the water consumption is pretty low. So here, these are diagrams based on the power plant distribution that from Tim Deal's report. He evaluated almost 1,300 plants, and you can see this is the water withdrawal in acre-feet per year. So in this diagram, you can see large water withdrawals in the eastern U.S., mostly once-through systems, and also along the coast. And this is acre-feet per year. And the total acre-feet per year was about 130 million acre-feet in 2010. And on the right, then, you can see in the next diagram, then, we show water withdrawal as a rate in gallons per kilowatt hour. And you can see that the high water withdrawals are concentrated mostly in the eastern U.S., where we have once-through systems. And the small triangles then represent the water withdrawals for cooling towers, which are much lower. And on the lower part of the diagram, you can see the average rates for different types of plants. So coal and nuclear plants have 30 to 40 gallons per kilowatt hour, whereas the natural gas combined cycle plants are about a third of that, because they include combined gas turbines with steam turbines, and it's about 11. Then the cooling towers then have much lower water withdrawals, less than 1 gallon per kilowatt hour. So here is the water consumption. Then these are much lower numbers than the water withdrawal numbers, and it's fairly uniformly distributed throughout the U.S. But you can get a lot of local variability then because of different types of generator technologies and cooling systems. And so the total is 3.5 billion gallons per day, or 3.9 million acre-feet. So here is the rate of water consumption then, and here we are showing steam turbine plants with the blue circles, and the size of the circles reflected the variations in rate, and the combined cycle plants then are shown by plus signs. And this is the average of the entire system. So you can see natural gas combined cycle is 0.12 gallons per kilowatt hour, and the cooling towers is 0.2 gallons per kilowatt hour, where it's slightly higher than for coal and nuclear plants. And this reflects the different water sources, mostly surface water sources in the eastern U.S. and a lot of unknowns in the western U.S. And then municipal wastewater or other sources scattered throughout and from treatment plants. And the water quality then along the coast, then we have seawater being used for cooling, and inland then it's mostly fresh water. So lastly, I just want to briefly talk about drought vulnerability of electricity generation. So 2011 was extreme drought in Texas, with about almost 100% of the state under D4 or exceptional drought conditions. And we're wondering why we didn't see any blackouts. So electricity demand in 2011 increased by 6%, and the water demand to cool that electricity increased by 9%. Meanwhile, the reservoir storage decreased by 30%. So we reduced water supplies available for cooling when we needed increased electricity demand. And so we looked at how the power plants adapted by looking at places where reservoir storage dropped below 50%. And we found that in each case they were able to cope with the drought. For example, on the top left there, they changed from a once-through cooling system to a cooling tower and reduced their water withdrawals by more than a couple of orders of magnitude almost. And this is because that power plant was built in the 50s when it was in drought conditions before. On the right, then they reduced their consumption by changing from a steam turbine to a gas turbine. And on the lower left, they finished a pipeline to bring water into the system. They couldn't finish it the previous year because it was too wet. So during the extremely dry period, or hot period in the early August, ERCOT also shed 150,000 megawatts of interruptible load to avoid rolling blackouts. So these are examples of the different types of strategies, and when you have a lot of different options, then you can be more resilient and less vulnerable. And increasing natural gas in the state has reduced water demand for electricity generation and increases drought resilience. So the yellow line shows the increase in natural gas generation capacity in the state around 2000 when they had the market became deregulated, and then the blue line shows the decrease in the consumption in gallons per kilowatt hour associated with that. So just to summarize then, how do water and electricity systems compare? So we see large differences in terms of storage and transport. And energy flow diagrams help us to understand the linkages between fuel sources, electricity, and end users, and emphasizes that there's a lot of wasted energy. The dominant controls on cooling systems are the dominant controls on water withdrawal, and cooling and generator technology are important for water consumption. The water footprint, 2010, 50% of water withdrawal was for thermoelectric cooling and 4% for water consumption. And in terms of vulnerability during drought, then if we have power plants that have more options, then that translates to drought resilience. And natural gas helps quite a bit because it can be a peaking plant, and also the combined cycle reduces water demand relative to traditional steam turbine plants. So I'll turn it over to Vince Tidwell now, and he's going to talk about for the remainder of the time.
Thank you, Bridget. That was great. So what I will do is continue on this general theme of water and electricity generation, and as Bridget said, a really great foundation in terms of has pointed out a number of places where water touches the electricity generation sector. And here, this is a report from DOE in 2013 where they looked about 5 years before and have noted all of the times where water has impacted different aspects of energy, and in this case, where water has caused power plant outages. And you can see that these, the lighter colored icons here, they're largely in the east in this particular case, usually due to elevated water temperatures. The one in Texas was a case where actual water supply for a small plant had an impact. In this case, we've also seen historically impacts on hydropower production. And just 5 years before 2013, you can see that a number of cases where hydropower was impacted by low water, and which was big enough to make the news. Again, another way that we see impacts of water on the electric industry through damage by extreme events, floods, storms, etc. You can see cases where wildfire have affected transmission. You have storms affecting transmission as well, storms putting out power plants, or even storms or floods impacting the pipelines and such that are delivering the fuels to the power plants. So a number of cases where extreme events have had impacts. And then we're also beginning to see impacts of water and water-related concerns on permitting of new facilities. And so just in the last few years across the board, we're seeing all kinds of impacts of water on our energy infrastructure, and particularly our thermoelectric industry. And so, you know, we've seen these issues. It's getting harder and harder to site new facilities because of the water requirements. It's very controversial, and we expect that these things are going to get worse and worse. But actually, this is a comment out of a report by DOE in 1980. Unfortunately, we didn't do much about it at that time. We had other issues that I guess were more pressing. So, you know, now we again kind of stand at that fork in the road and decide what path we want to take, and what that future pathway relative to how our electric power system is going to evolve, and to what extent we integrate water into that. And so I believe that I know there are many opportunities that we can take to a more resilient and sustainable energy water future. And that's really what I want to focus in on for the rest of this afternoon is looking forward and some of the steps that we can take, and basically a rough outline. A few of the things that I want to take a look at is integrated planning, fuel switching or changing from one fuel type to another, looking at alternative water sources for our electric power generation, and then research. Where's DOE going in the near future with this energy water nexus? So first I want to begin by looking at integrated planning. I think that's probably some of the lowest hanging fruit that we have. But, you know, unfortunately, it's one of the things that we probably do least, and that's bringing water managers and energy managers together and really collaborating on long-term planning. This is a case that we were involved with where we actually did bring the energy managers, in this case, the Western Electricity Coordinating Council. They manage the electric grid out in the western U.S., along with the water planners from the West, particularly the Western States Water Council, as well as the Western Governors Association. And then DOE helped provide support to allow some of the labs to help work with WEC and the water managers to bring and integrate water into their long-term transmission planning. And by long-term here, we mean 20 years, helping them with decisions about where do we put that next power plant, where do we string that next power line. And actually, if you remember back to what Bridget was saying earlier, she had the pie charts of water use, water withdrawals, and consumptions for the entire U.S. Well, this is withdrawal on the left for just the WEC service area, so most of the western United States. And you can see a very different picture here. Irrigation totally dominates. Thermoelectric's only about 2% of the picture. The reason being, because there's a lot of irrigation, but more importantly, as Bridget was talking about, out west, mostly use closed-loop systems, so much less of the open-loop systems, which tend to withdraw large quantities of water. Alternatively, on the water consumption side, thermoelectric is tiny, less than 1% of the overall water consumption. So this was a real sticking point and an educational point, if you will, for the energy managers. When they saw this, they thought, why in the world do we need to worry about this? It's all about irrigation. Well, in the West, we're not so worried about who already is using the water. They already have water rights. It's that next use of water, that next drop of water for the new development. Where's that water going to come from? And that's why this whole water issue is important to the thermoelectric power, particularly in the West, because it's that small slice of the pie that's growing, thermoelectric, municipal, industrial. And so once we helped them to understand that, we could move on with the project. The way it started and kind of the approach we took is, there's a lot of uncertainty about the future. So developing future scenarios. In this case, 5 different scenarios were developed. One's a reference case, largely with the energy in terms of electric power generation, kind of following trends as they're going today. Then there were 4 others which address the 4 quadrants here in this quad chart between higher economic growth or a little slower economic growth versus technology innovation, kind of current patterns versus much more of what they call a paradigm changing, where there's a real move largely in their mind to much higher penetration of renewables largely. And so scenario 1 and 3 are kind of current technology patterns with high and low growth. Scenario 2 and 4 were, much more green, much higher renewable penetration, and both of these cases also included a strong, at least in their mind, a strong carbon dioxide emission standard or carbon cap. So with these scenarios, basically that helped define the inputs to an optimization model, a capital cost expansion tool, which was used to co-optimize between new generation additions as well as transmission additions. And so it was then constrained by a large number of factors, not just water. It was constrained by energy costs for both fuels as well as technology and how those costs evolved over time, how policy would evolve in terms of carbon caps, certain environmental policies about where, power lines could go, policies in terms of renewable portfolio standards, et cetera. So many, many constraints on the model. Water was one of them. And so basically, using these scenarios, it would look forward. It would decide where to put, a new power plant. It would decide if it needed to build more transmission capacity, and it would continue to iterate until it got the most optimal solution. So then one of the important inputs then was, as Bridget was talking about throughout, is that different types of power plants use different amounts of water, and as well as the type of cooling system. So you can see once through, cooling pond, recirculating. In this, we just assumed recirculating cooling because of the constraints, the 316B rule that really constrains new use of open loop power plants. So we assumed all would be recirculating or dry cooling, but the dry cooling was too expensive. It never showed up in the model. And then you can see the difference in consumptive water use here, the red columns for different types of generation, particularly nuclear and coal, but you can see how much lower down here natural gas, PV, solar, or wind are almost zero. So you can see that by just making a shift from coal or nuclear to natural gas or wind, solar makes a big difference in water use. And this we will actually see plays out very important as we move throughout. But then we also had to set this constraint on our system. Once we knew how much water different power plants were using, we then needed to set a constraint in terms of how much water is actually available for new use. And so we worked directly with the water managers. They help provide information on various measures of water supply, measures of how much water is being used already in the basin. And this is really what kind of differentiated what we were doing in terms of these water availability is the water institutions, the water compacts, water rights, Indian water rights, administrative control areas, and all of these other measures that control, even if there's physical water out there in the river in front of you, you may not have access to it. So these institutional controls help provide that information. And so working with these water managers, we were able then to develop water availability metrics. These are actual what the state would say how much water is available for new development in these regions. And so we mapped, working with the states, we mapped this water availability at a HUC 8 level, so about 1,200 watersheds across the West. We did that for 5 different sources of water, for basically fresh surface water, fresh groundwater. Appropriated water is water that you would be buying off of a farmer and moving it to a different use, municipal wastewater, and then brackish groundwater. And so basically areas that are white are areas that the state says there's no additional availability of that source of water. Blue would be pretty high availability of water, and then the green is something on the order of what you would need to build a combined cycle plant, natural gas combined cycle plant. So you can see here for fresh water and groundwater, there's not a whole lot of fresh water available for new development. These others, there's more distributed supply, but again kind of limited in certain areas. Here, we've also estimated how much additional new water might people be demanding for growth, say, in the municipal or industrial sector. And so, again, the states helped us do this. The white areas are where there's no real growth projected. These are rural areas, but you can see the municipal, like the Phoenix area, Dallas-Fort Worth, some of those areas that are growing pretty quick, or projected to grow pretty quickly, LA, et cetera. So we use this information, but also recognizing that we have these different sources of water, that they're not created equal. It's going to cost more to use some of these different supplies of water. So we took a shot at creating a relative cost of water, which included the capital and operating costs to, if we needed to lift the water, to buy the water in the case of appropriated or municipal wastewater, and then also if we needed to treat the water to bring it up to a standard that could be used in the power plant. And so you can see the brackish water tended to be the highest, the more reddish color. Municipal wastewater tended to be the next most costly, and then on down. So we put all this together, basically created a supply curve, and then was for each one of those HUC level basins, and then gave that to the WEC, and they were able then to look at their different scenarios and basically decide where they would put their next generation. What was interesting is that largely, regardless of the 5 different scenarios that you see here, they all largely have 3 things in common, that really the only new construction was natural gas combined cycle, wind, and solar. This had to do with a variety of policy constraints and cost constraints, and also uncertainty about, future possibility of carbon caps and other things. And so largely all the new construction were from renewables or natural gas. The other 2 important occurrences were for scenario 2 and 4. These involved the added carbon cap. And in these cases, that you can see that there's no more coal. The purple here, there's no purple. In other words, all the coal is displaced in these particular scenarios. So in other words, there's no more coal generation. And so this has a big impact overall on water withdrawals. You can see that from 2012, that all the cases end up with a lower withdrawals. Largely that's driven by reduced saline water withdrawals on the coast, largely due to California closing or retrofitting all their coastal plants. However, for the scenario 2 and 4, where they really backed off on the coal, we see a big drop also in freshwater use, almost a 70% withdrawal or cutback. Consumption, on the other hand, you see that 3 of the scenarios increase consumption by about 30%, while scenarios 2 and 4, where we displace a lot of coal, it drops by about 30%. So it really matters which scenario you're looking at. So this kind of gives the high-level view, but what about watershed by watershed? Because we know that water is really a local issue. And so basically, these are the 5 different scenarios. And from here, you can see the different hubs where the WEC, the capital cost modeling was done. And there, the water constraint, whether they would look to put new generation at each one of these hubs based on, the demands and whatnot, and then would look to see if there was enough water there. There were only a few cases, the cases where you can see where it's the dark outline here. These are the only cases out of hundreds of hubs where they did the analysis. There were only 8 cases where they actually would have built more thermoelectric power in these hubs had there been more water. So only 8 cases where the water constraint kicked in. And so when I first saw that, I was a little alarmed. I kind of thought, well, this didn't work very good. You'd think in the western U.S. where water is so limited that this water constraint would be much more important. Why is it not showing up? Well, actually, as I thought about it more and more, what has happened is that water is having an impact on the planning in a very different way, in an indirect way, if you will. That the decisions that were being made earlier about what type of power plants were being built, the fact that they're being natural gas combined cycle, a lot of PV and a lot of wind, meant that the new demands for water were highly reduced over, the normal coal or nuclear. So overall, the new water demands were somewhat limited over what we might expect otherwise. So this fuel switching, if you will, made a huge difference. The other is just the topology or topology of the system, the fact that, we have the demands, they're broadly distributed, there's certain policies in place about where you have to place the power. The transmission system itself also puts a constraint on the system, which tends to distribute all that new generation as well. So again, these two things together, the choices about the kind of power they're building as well as the distributed nature of where the new power is needed, tended to help offset the impacts on or the need to really constrain where that new generation is placed based on water supply. So that was kind of an unexpected result. We then took those, from those hubs, we were able to map around to the actual watersheds based on where the current generation exists associated with those hubs. And so here we were able to map out the future demand for new thermoelectric power generation. And so the warm colors are where the net water use increased. Gray is where the new demand is actually equal to the retirement of old water use in the thermoelectric industry. And then the cool colors are where there's actually a net decline in water use overall for the thermoelectric industry. And so you can see that scenarios 1, or the 3 scenarios referenced in scenario 1 and 3, overall there's an increase in water demand as we saw earlier. But 2 and 4, you can see large areas that actually there's a reduction in net water use by thermoelectric power generation. These are the cases where a lot of the coal or all of the coal is being displaced and being replaced by much lower use renewables and natural gas. So 2 important takeaways from this. One is that at least where there's a strong carbon cap and the coal begins being displaced, here you have the opportunity for the thermoelectric industry to actually be a net provider of water for future development in other sectors as they move away from coal and move to other lower water use options. The other is that you can see these cases where it's outlined, where the watershed is outlined in black. These are the only cases where the demand for future water for thermoelectric development exceeded 10% of the available water supply. So in other words, there are only a handful of cases where the demand for new water exceeded more than 10% of the existing available water. So in other words, we can build out, we can continue to expand if we do it right, if we integrate, if we talk, if we consider carefully what the impacts and work together, that this integrated planning can help reduce impacts overall on water, on impacts of the thermoelectric industry on water resources. So from this case, and final thing here is that, but there is going to be a higher cost, and you can see here the warmer colors are higher cost. And you can see that in most cases, these higher costs are associated with the California. In part, that's because of the more and more that, a lion's share of the electric, new electric generation is located in California. But more importantly, it's because California has policies in place that limit use of fresh water for new thermoelectric development. So they are having to go to non-traditional sources of water, which are going to require some treatment and some other costs that are going to drive the cost up a little bit more. But anyway, you get an idea of this interaction of both, the constraint of water as well as the overall impact on cost for water for thermoelectric development. And you can see no cost out here in the western U.S. because a lot of the water that was being freed up from those coal plants is now being put to use to generate the coal. I'm at the gas, the new gas generation. So here, this particular case showed, how, integrated planning and putting in, thinking about water as part of the planning process can have an impact and reduce the impact on water resources. We saw the important role that moving from coal to natural gas and renewables has a big impact on lowering water use. And then finally, here we're also seeing where the role of alternative water supplies are having to play in to meet some of the future demand as well. We're also beginning to move into the east, and so we're now working with water managers in the east to map out water availability. One of the big differences, and we haven't quite finished, these are the gray states we're still working on, but you can see a bunch of these outlined watersheds in the east. What was kind of interesting is we worked with the states. They were saying, well, we're not going to say that, there's a hard and fast limit on the water supply in this particular basin, but there are some additional permitting and concerns in those basins that you're going to have to deal with. So basically that's where we kind of got into outlining some of these basins and just recognizing that in certain cases there are additional constraints on use of that water in those basins. Also mention that we're continuing to do some of this work in terms of trying to understand, what the impact of this water constraint might be on ultimately the power generation portfolio. And so what we've been doing is working with NREL. They've taken our water availability data for different sources of water and the cost, and integrated that into their REEDS model, the Regional Energy Deployment System model, which helps project evolution of the electric generation portfolio over time with different assumptions about technology costs, water constraints, and environmental constraints, et cetera. And while I won't try to go in and explain the differences between all of these, the idea is that, we're able to run a series of experiments and be able to see what a set of different constraints and different assumptions can do concerning what that those constraints and to what extent water plays into those constraints, and the cost of water influences how that power generation portfolio may evolve over time. And so there should be some papers coming out very soon detailing some of our results there. So now I want to switch gears just a little bit and talk a little bit about alternative water sourcing. And so in the example before, we talked a little bit about, thinking about different sources of water for future thermoelectric power generation development. Here we're looking at existing power plants, so roughly the 1,200 power plants that exist, thermoelectric power plants that use fresh water. And so the idea would be is, how hard might it be to retrofit these power plants to get them away from freshwater use using either dry cooling municipal wastewater or brackish groundwater? And so basically what we did is we went around, we looked at it, first decided whether there was availability of municipal wastewater or brackish groundwater, and then calculated the cost, the capital and operating cost, et cetera, to do the retrofit. And so from there, we did this for every power plant. And you can see that these are the curves for every power plant. You can see that dry cooling was the most costly in all cases. Then that wastewater tended to be the cheapest, and then wastewater, but I meant brackish water. But you can see in many cases there just wasn't that water available for use. And so the red line here is the least cost alternative, and really the thing that struck us that over 50% of the existing power plants could be retrofitted at a cost that's less than 10% of the current operating cost or cost to generate electric power at over half the power plant. So there's some low-hanging fruit there. And so you can see here in this lower graph, which power plants went which way. Largely, those that went the dry cooling way is because there was a lack of water nearby. More importantly, though, is that from here you can see that the cooler colors, the blues, the greens, the yellows, these are the lower cost overall to do the retrofit, and you can see that it's largely out west, and largely, or that many of the basins here that are outlined in red are basins where there's limited water supply. Also, where the lines are areas of rapid growth. So in many of the areas experiencing rapid growth and limited water availability, or areas where some of these lower hanging fruit, less costly retrofits may be available. So something to think about is, again, another opportunity for kind of making a more sustainable energy system. And finally, I want to finish up real quick and where DOE is going with this energy water program. As many of you, and Bridget already noted, there was a report in 2014 that the U.S. Department of Energy put out on energy water. What it really boiled down to is that it lays a foundation of where more work is needed and where the opportunities are, and 6 basic pillars, but basically they can be summed up in 3 things. We've got to develop technology to lower our water use in the energy sector. We need to improve the energy efficiency of treating water so we can make more sources of water available, and then we need to develop tools to better understand the reliability and resilience of our energy water systems and prepare for those. And that really at the base of all these is data modeling, analysis, advanced technology, and we also have to be engaging stakeholders and looking at policy. And the idea is, a focused national program around the data, the technology, and engagement, but also that we'll develop these regional clusters where some research is being done, but the real focus here is doing experiments and tests on real problems in basins, working directly with stakeholders. And so this is kind of the approach that they're wanting to take. The President's budget has outlined, or the proposed President's budget for FY17 has several different key activities that are planned in this data modeling area, a federated energy water data system. So, again, not recreating things that are already out there, but trying to bring together existing data sets, particularly where they interact in this energy water area. More work on better models for integrated assessment, IEV, et cetera, and then a framework for integrating multi-system, multi-scale models into a framework that are interoperable. Technology, we've already, are big areas, low carbon, low energy, low cost desalination, other treatment, particularly around produced water, looking at better energy efficiency in our water and wastewater systems, and also energy recovery from wastewater systems, and then water efficient cooling in our electric power generation. So these are all activities that, depending on where the administration goes in FY16, we hope to see some real new funding in this area. Finally, with engagement and policy analysis, the big area would be these regional scale data and modeling and analysis test beds, where we get out and do experiments in working with the stakeholders in specific regions, and hope to establish 3 of those. There was also, that I don't say on here, a new CERC for China, a Clean Energy Research Center focused on energy and water. So that's an international project that was awarded to a group out of California, Berkeley Laboratories, Stanford, and University of California, Berkeley. So, and some others. And so, anyway, this gives you a high idea of where DOE and some of the things they're really wanting to focus on in the coming near term. About $100 million, and most of that's new money is set aside in this 2017 budget for the President's budget that's being proposed. So, we're talking about potentially a pretty big uptick in that area. So just ending up, what we've talked a little bit about is kind of looking forward. what are some of the things that we can do to better prepare ourselves, be more sustainable in this energy water area, particularly as it applies to electric power. We've talked about integrated planning. We've talked about being cognizant of the kinds of power plants, this fuel switching, moving to lower use natural gas or renewables. Also the idea of using more and more non-traditional water, wastewater, brackish water, both with new plants or even retrofitting some of the existing plants. And then also talked a little bit about some of the new research areas. Here's my contact. You can get some of or all of the reports and the data that I've talked about here, and here are some references for what we've been doing. So with that, I will close and turn it back over to Emily.
All right, thank you so much, Vince and Bridget. So at this time, we will go ahead and take questions from anyone that has one. And if you're on the line and connected to the webinar, you can go ahead and type your question into the chat box. We will wait just one moment to allow people to put their questions in. All right, it looks like you guys were very thorough. The chat box looks pretty quiet right now. Bridget, do you have anything else that you'd like to add?
No, I just reiterate, I guess, Emily, that all the material will be uploaded on the QASI website, so recorded sessions and also PDFs of the presentations if anybody is interested.
That's correct. So I just put the link to those presentations into the chat box as well on the QASI website. So let's see, looks like there's a question from Hisham here who says, thanks for great presentations. How will climate change be incorporated into the Energy Water Climate Nexus framework?
I can take a bit of a stab at that. I know as far as where DOE, particularly the Office of Science, they're looking to start up a couple of new projects in this space. Well, actually, I would say 3 of them, as I kind of very quickly alluded to. One is working across not only the DOE labs, but this would be extended out to other agencies and academia, interest in looking at existing models that are out there at a variety of scales, all the way from integrated assessment models, regional assessment models, down to specific tools used for modeling particular infrastructure, and looking at the inclusion of water or energy in either of those, in any of those models, and the coupling between them. And so I think there'll be some calls for research and looking how to couple those. And from there, ultimately the idea is then to develop a coupled framework to bring various infrastructure scale models together with a variety of, like I say, the regional and integrated assessment modeling, all the way up to the global climate models, and developing tools to be able to drive the impacts of climate change down to the direct impacts on our energy and water infrastructure. And beyond kind of doing more research on the basic pieces, coupling these models so that we can begin to see what some of the feedbacks are through the system, and then actually implementing these in a series of basins where we work directly with stakeholders to address some of their specific issues.
Okay, any further questions? All right, well, if there are no other questions for today, I do just want to say thank you again to Vince for presenting this afternoon. And Bridget, thank you so much for organizing this session. It was a really great and informative session, and we got a lot of positive feedback on it. So I encourage everyone to check out the recorded presentations if you haven't already. And the next quasi-Cyberseminar series will take place in the fall. So be on the lookout for information about that coming out later in the summer. So again, Bridget and Vince, thank you so much for presenting today, and everyone have a happy Friday afternoon.
Thanks.
Thank you, Emily.